So it's a pleasure to have Padmanath with us, talking about understanding different aspects of QCD from Lattice. And Padmanath has been doing very interesting work on charm and bottom tech. He was one of the first authors who published a work on this double and triple charm baryons, from lattice calculations, and that was one of his very highly cited work. Now he's also working on heavy quarks and also scattering upward channel and lot of interesting and he will tell us more about his recent works. Please, Padmanath.
Okay. Thanks, Chandan. Thanks, Chandan and Sanathan for inviting me for this talk. I will start the talk by motivating you all on why I am interested in subnuclear physics. You all can see my screen, right?
Yes.
And my pointer.
Yes.
Yeah.
Okay. So I will start by motivating you all by why I am interested in subnuclear physics and why I use lattice quantum ChromoDynamics for these studies. So let's start with something that we all have heard about. The Nobel Prize in Physics for the year 2013 was given for this BEH mechanism, Brout, Englert, and Higgs mechanism. Of course, it was given only for Englert and Higgs since Brout was no more. He was unfortunately have passed away a year back or so. So the prize was given for this mechanism that generates, that is believed to generate mass for the fundamental particles that we know of. So what are these fundamental particles? This is what I list in the bottom of the slide. There are different categories of fundamental particles: quarks, leptons, gauge bosons, and Higgs field. In the quark sector, there are 6 different flavors of quarks, 6 different flavors of leptons, and there are 4 different gauge bosons that mediate the interactions that we know of, and the Higgs field. And we can already see that some of the fields I have colored while others are represented in black, because these fields that are colored are of my interest. Particularly, okay, of course, top is not of my interest in this current talk, or probably near future we may not address top. But the remaining up, down, charms, strains, bottom quarks, as well as gluons are the fields that are of interest in my talk. Now let's view the universe in a different angle. We know that most of the visible matter that we see, visible matter in the universe, the mass of most of the visible matter is composed of protons, neutrons, and electrons. Now we also know that protons and neutrons are approximately of the same mass. While electron is like 1 in 2000 mass of a proton or a neutron. So that basically means that most of the mass in the visible universe is coming from proton and neutron, which are generally correctly called as nucleons. And why I specifically say this nucleon is because most of my talk will generally refer things as nucleons, because we don't consider QED into picture. So let's keep this word in mind, nucleons. Now let's look at the mass of a nucleon. You can, which I quote from PDG. You can see it is around 1 GeV, 938 MeV, close to 1 GeV. While the U quark mass and D quark mass I have quoted again from PDG, which is like 2 MeV and 4.67 MeV. So that basically means that more than 99% of the mass in the nucleon is not originating from BEH mechanism. Remember, nucleon is not a fundamental particle. Only the Q and D quarks are fundamental particles. So that basically means most of the mass in the nucleon is not originating from BEH mechanism. Already is interesting. Now let's compare this with the thing that we all are familiar about, a hydrogen atom. We know that the mass of hydrogen atom is around 1 GeV, which is basically the mass of proton. The electron has very little mass, and its binding energy is like 13 eV, minus 13 eV. So that is like several orders of minus 13.6 eV. That is very large orders of magnitude smaller than whatever the mass of hydrogen atom is. While in this case where we are dealing with proton, here the situation is totally different. We have the particles that proton is composed of, which are like very which are like a few MeV, while the proton mass itself is like 3 orders of magnitude larger. Okay, so that clearly says there is some, this is some unconventional binding energy, and there is some non-perturbative nature happening here. By now we know that these interactions which we refer to as strong interactions are at play. And we also know, and now the theory has developed so much that we know that quantum chromodynamics is the theory of strong interaction for the discovery of asymptotic freedom. So basically a pattern of decreasing interaction strength with increasing energy in the theory of quantum chromodynamics was discovered by these three people, which led to awarding them Nobel Prize in the year 2004. So what this says is, what this property of asymptotic freedom says is that at very high energy regime, quarks tend to be free. Quarks tend to be non-interacting. So that basically is what is said to be very asymptotic freedom. While at low energy regime, it could be quark confined, or it could be confined. All the quark fields could be confined. So this is why I classified two regimes, where there is a high energy regime where there is asymptotic freedom, or the quark tend to be free. So that basically means that the interaction strength is very small. So in that kind of scenario, one can try to study this kind of theory by some perturbative approach. While there is another regime, low energy regime, where the quarks tend to be confined, and the effective degrees of freedom that we see are basically hadrons. And in that regime, the interaction strength is too large that we cannot use any perturbative techniques. My talk basically will address hadron spectrum calculations from QCD. Various different there are various different problems with hadron spectrum determination itself, which I will get into in the course of my slides. And basically all the technique that I use in this is basically lattice QCD, which is a non-perturbative first principle technique. So we try to solve for QCD from the first principle. Actually try to solve for QCD using numerical techniques. So before we actually get into all this, let's briefly go through the action theory itself. So here I put the QCD action where maybe I should use slides, sorry, cursor. So here is the QCD action where you have the gauge action here and the fermion action here, which has a mass term. The derivative here, which is standing for the kinetic term, which is a gauge covariant derivative, and the gauge covariance, this A is basically the gluon field, which brings in the interaction between the fermions and the gauge fields. Now you can see that the field strength tensor is represented like this, and the non-commutative property of these gauge fields for QCD, which is an SU3 gauge symmetry. So you have a non-commutative term that comes into picture, which gives all this non-perturbative behavior in the hadronic scale. Now, what is more interesting for the rest of my talk is this. So let's consider the massless limit. We have a symmetry for this action in the fermion sector, where if you have NF flavors, there is a symmetry which is SUNFL, which is standing for left-handed, and SUNFR, which is for right-handed fermions, U1V cross U1A. The U1A is broken by the invariance of fermion integration measure. So which is this part is not really interesting for us. I just mentioned this so that you don't feel this has been neglected in discussion. But this part is not really important for what I will be discussing later on. Now, more interesting part is this SUNFL cross SUNFR. So we know from experience that there are no energy degenerate parity partners observed in the hadron spectrum. That clearly means that the SUNFL cross SUNFR is broken, because if this is if the symmetry is there, then there should be parity partners in the spectrum, but this is not observed. And we also know that there are really nearly massless Goldstone-like bosons, which basically implies that if you rewrite this symmetry in terms of SUNF axial cross SUNF vector symmetry, then the SUNF A should be spontaneously broken. Near massless I say in a second, but yeah, basically if you forget for the time being the near part, there are massless bosons in theory, which indicates that the theory is spontaneously broken at hadronic scale. Okay. Let me also remark one point here, which is also not important, but since I show a slide for the finite temperature studies from Lattice QCD, this might be useful. So I say here that the SUNF A is spontaneously broken at the hadronic scale because there is presence of Goldstone bosons in the theory. So at the hadronic scale is important. So we see these kind of Goldstone bosons at the hadronic scale, while at high energy regime where there is asymptotic freedom, we don't see any more hadrons. So basically all these symmetries should be recovered. This is what we expect. Okay. So this is just a remark which will be useful for a later slide that I will present. Now let's move on to this near massless part, which I have italicized here. So we know that quark masses are non-zero. So that basically means that SUNF A should be explicitly broken. I quote here the quark masses from PDG. I quote only the central values because that's the important thing for this discussion. If you take a typical hadronic scale as mass of proton, for example, 1 GeV, then you can clearly see that the mass of U, D, and S quarks are very small. Okay, S is relatively large, but still can be considered small if you take a typical hadronic scale of 1 GeV. While MC, the charm quark mass, the bottom quark mass, and the top quark mass are really, really heavy. So this is a way of classifying U, D, and S quarks as light quarks. So for these kind of systems that have these kind of quarks, we expect the effects of explicit symmetry breaking on the light quark hadrons are relatively small, or the systems where there are light quarks are relatively small, while for those systems where there are C, B, and T, for example, for the timing you can forget about T because T don't appear at all. So for systems, for hadrons which have C and B quarks, these are referred to as heavy quarks. There the chiral dynamics is almost absent. So these quarks are called as chiral quarks, chiral because they have very small mass and they nearly respect these chiral symmetries. While these quarks, since they have very heavy quark, since they are very heavy, they don't show any chiral properties. So that's why they don't really have any chiral dynamics due to this large explicit symmetry breaking. Okay, so that's why we call C and B quarks as heavy quarks. And most of my calculations are focused on heavy quarks because they are quite nice to study. This is what I discuss in the later part of the next slide. So once you have a heavy flavor tag in a hadron, so that basically hello, yeah.
Sorry,
hello?
Can I interrupt just one question?
Yes, please.
So this U1V that you mentioned in the previous slide.
Yes.
So what is the consequence of that?
It's the baryon conservation. Yes.
That's baryon number.
Yes, it's preserved.
Okay. All right. Thank you.
Yeah. Okay. Yeah. So it's preserved. So that's why I did not. So the most interesting part was the first two. That's why I discussed mainly this. Okay.
Padmanath,
yeah.
Can you please go back to the same slide again where you have?
Yes.
Yeah. So here you are saying just below that there is to resolve this issue of not having parity partners, you have this spontaneous symmetry breaking mechanism, right?
No, actually not for the parity partner, but the presence of Goldstone bosons indicates this is spontaneously broken. But the absence of parity partners, okay, this is the way I understand. So the absence of parity partners just means that this is somehow broken.
And what happens, I mean, if you can restore the symmetry at high temperature, what happens? The parity partner should be...
So if you restore, okay, so yeah, if you restore the symmetry, then you should expect to see parity partners. For example, let me take an example of, say, Nucleon itself.
Yeah.
In low energy, the Nucleon parity partner is around 1500 MeV, 1.5 GeV, while the mass of proton is 1 GeV. Now, if you go to high temperature, then one expects the symmetry is somehow is getting restored. So you expect the splitting between this nucleon and its parity partner to decrease.
Okay.
This was one of the studies that we did in the past in 2013, and we saw that there is already an early onset even before the confinement deconfinement transition in an SU3 basically sequence theory. Yeah. But yeah, I am not going to discuss that.
Yeah, sorry to interrupt. There are some models which talk about this colored hadrons above the critical temperature.
What hadrons? Sorry.
Shuryak and some other people are saying, do they include these parity partners in the pressure equation of state?
I'm not entirely sure about this. Yeah,
Okay, we can
I don't know.
later.
Yeah. Yeah, the finite temperature is not really my field of expertise. Or maybe I am not aware of these calculations. Yeah, sorry.
Okay.
Yeah.
Sorry about the baryon number that you just mentioned. So when you spontaneously break the chiral symmetry, are you going to ensure this baryon number is left intact, or is that not something that you would check?
Baryon number. Okay, so if the baryon number is not intact, then symbol nucleon should decay somehow.
No, but when you do your lattice simulation, so what about baryon number? What if that also gets spontaneously broken? Is that possible, or
no? It is not. No.
No, why is that?
Because it is preserved, right?
How how do we know that?
Because okay, let's compute a simple nucleon correlation function. Okay, this I am already getting into the technical details, but if you simply compute a nucleon correlation function in the lattice, since we do a Euclidean, since we work in a Euclidean spacetime, we get to see a exponential fall of the correlation function. Okay, because okay, in the Minkowski space, you have an e raised to imt at very large times for ground state, while in the Euclidean space you have a e raised to minus m times t. So that basically means this is an exponential decay. Now, if suppose the baryon number was not conserved, and if you are constructing a nucleon correlation function, then the nucleon should decay somehow. If that nucleon decays down to some other state which is smaller than its energy, so then that basically means that the correlation function will, the correlation function will fall at very large times will have a mass which actually goes down and down and down. It should actually saturate. If you look at, okay, can I go to one later slide to explain this?
Okay, thank you. Yeah, got it. Yeah.
Maybe because if I get into that slides, I can.
No, it's fine. You can come back to it later. Yeah, I think I got the message. Yeah, thanks.
Yeah. Okay. So where was I? I was here. So I was discussing why these heavy quark systems are important or interesting. With a heavy flavor tag, there is little role for chiral dynamics, as I said. Of course, if you have a system which has only heavy quarks, this is the best. But if you have some light quarks in it plus heavy quark, then still it is a heavy flavor tag. So you can study the dynamics of confinement mechanism, etc., in very much detail and very much nicely than with respect to light quark systems or systems that has only light quarks. Okay. To also motivate you in a different perspective, just take the last decade. There are 36 different new quote-unquote conventional heavy hadrons discovered. What I mean by conventional are those heavy hadrons which are well understood in terms of well theoretically understood. So they are understood in terms of why they should have these masses, or why they should have these decay widths, or why they should have these kind of decay channels, etc. So all these 36 hadrons includes various different kinds like quarkonium. Quarkonium means a quark and an anti-quark, basically a charm and anti-charm, or bottom and anti-bottom kind of heavy hadron. Open flavor mesons, by that I mean when you have a charm quark and a light quark in it, or a bottom quark and a light quark in it, there is several baryons that are observed. many more are also expected to be discovered in near future, because if this is the way it is going, there will be many more that will be discovered that are also expected. We have also predictions that I will come into in some of my later slides. More interesting is the sector of exotics. There are a lot of states, like approximately 40 or so candidates that are observed in experiments. Theoretical understanding. Okay, I will get into detail in a moment what I mean by lack good theoretical understanding. But just briefly give you an idea. So they are not well understood in terms of the quark content. They are also not understood in terms of their quantum numbers. Not just from not just theoretically, but also from experiments. It is not clear. Many times it is not clear what are their quantum numbers. Many of them has resonance properties or properties like decay weights or their decay channels. These kind of details, they are not explained properly. They means we could not explain the their property observed properties very well. Or there are also properties that are expected but that are also absent in some those. So that's why these are called exotics. Okay, and most of these candidates, okay, 15 of them, 15 out of these approximately 40 candidates are already confirmed by PDG, and most of them exist in the charmonium sector. So that's why charmonium is very much interesting, and I will be presenting results mainly on the charmonium sector, because since this is interesting, I have been working on these kind of systems. These are also very much advantages for BSM physics, which I will talk in the future plans. Beyond standard model physics, I mean. So let's get into some of the
quick question. So why is it only in the charmonium sector, most of them? Is that because of the energy, limitation, or why is that?
Okay, charmonium is easy to scan actually. Bottomonium, okay, it could probably be existing in the bottomonium sector as well, but bottomonium is yet to be scanned in detail. There are also candidates in bottomonium sector. In fact, actually, there are really interesting candidates in the bottomonium sector. If you look into, there are charged bottomonium-like states. So if you have a quark anti-quark, bottom and anti-bottom kind of system, then you expect the electric charge to be neutral or an electric charge to be zero. If you look into, you can see that people have BESIII, for example. BESIII are the people who really find out these things. So, so they have observed these states which have charge in it. So that basically means that there should be some other additional quarks in it which gives you non-zero charge. Gluons are electrically neutral, so basically that means there should be some additional light quarks in it which gives the non-zero electric charge. Okay.
Yeah. So you're not interested in looking at this one charm and another light quark, those kinds of systems.
Yes, I am also okay. Okay. We are interested in it, but yeah, the main reason why we are interested in charmonium is because this I will show a plot at later point of time.
Okay.
Then probably you will be means okay. Of course, there are interesting aspects in one charm and a light quark sector as well, but this is very limited. There are not many observations till now, and there are so many uncertainties there as well. Of course, we are interested and we can do it, but it's just 10 years of research, so I still did not get enough time.
Okay, thank you.
Yeah. Yeah. So then let's move on to why this why we need a non-perturbative approach. So first principle calculation using perturbative techniques. This cannot be done at hadronic scale. It is already clear. Just to highlight, let me read out what Godfrey and his group said in this regard. Therefore, to study these systems, mainly the heavy hadron systems, we must, for the present, rely on models which are a mixture of true QCD and phenomenological treatments of confinement, which are motivated by QCD. We call such models soft QCD to remind ourselves both of their rigor and their region of applicability. So they work with a lot of approximations, particularly highlighting those aspects of the interaction which are important to reproduce whatever we get to see. All these kind of phenomenological models. Okay, basically these classify into various different categories. So I just highlight some of them that I found interesting. So there are these class of models called potential models, where they try to construct a potential for these heavy hadron systems. This you may have heard of this Cornell potential, who actually first came up with this method, where they included a Coulombic term for a potential means 1 by R, and a linear term is basically an alpha times R, plus other interaction mechanisms. Excuse me, I'm getting an echo. Hello? Thanks. Okay, so these kind of potentials are used to study these excitations of study the spectrum of heavy hadrons. In fact, mainly they were earlier studied for low-lying heavy hadrons. Calculation is Baryon and Roberts from 2008. These are also applied for light baryons. This can be because Baryon is already in Baryon is already spontaneously broken, so you need some other techniques. So these kind of techniques, these kind of things are studied using effective field theories such as chiral perturbation theory for light hadron sector. Similarly, for heavy hadron sector, there are effective field theories such as non-relativistic QCD or heavy quark effective field theory. Even there are heavy hadron chiral perturbation theory, etc. I'll not be discussing all these things because these are not the part. These are not the things that I expert on, nor so and also it's not just about spectrum and understanding the fundamental degrees of freedom in the theory. One can also study the thermodynamics of these systems using models such as hadron resonance gas, Lambuja analysis, etc. Thing is, actually all these models approximate things, approximate the features of the interaction that are interesting for whatever is to be described. So this is what all these phenomenological apparatus do. So they are really quite powerful tools to understand certain aspects of the interaction, and this includes a lot of varying degrees of approximations in each of these models. And plus the main disadvantage is that there are several parameters to tune in most of these models. So basically that reduces the predictability of these models. Just to highlight this, for the exotic sector, these kind of approaches has been people are using these kind of things, and I'm just quoting one person who is a leading scientist in this regard. He says that it is becoming increasingly clear that no single theoretical paradigm all greater than 40 heavy quark exotic. So that basically means that it is clearly means just with phenomena not sufficient for us to understand what these exotics are or what the nature of these exotics are. To give you a brief picture of lattice QCD, lattice QCD is a technique of putting the QCD theory on a discretized spacetime or lattice QCD. This is a non-perturbative first principle approach. One can use it all the way from low energy regime to the high energy regime. So you don't really have to worry about the first application, although was in the strong coupling limit, but basically inspired for all these lattice QCD activities that are going on these days, was to explain that one can prove in the strong coupling limit with a lattice, one can prove that is actually a linearly rising at very large distances. So that basically means the quarks are confined. Explained later on. But yeah, let's visit some remarkable lattice research just to motivate why I am using lattice technologies to study whatever I am studying. Okay, so let's visit some lattice QCD success stories, starting with QCD coupling constant cell. So what I show is a summary plot of strong coupling constant from various different techniques. See, most of the lattice number is at the bottom region. The blue shader region is the world average from PDG, while the yellow shader region is average from each individual sector, each individual. And the bottommost thing is the lattice determination. Lattice also determines alpha coupling constant not just in one way. They people compute it in various different ways. For example, one can compute it from the, for example, one can also study from something more technical like a step scaling procedure. These kind of procedures. The second one that I said, one can even get the alpha s up to like means alpha s at electroweak scale itself, this mz square directly. So that's why lattice estimates in this regard are very precise, as you can see it already. It says the power of lattice calculations in this regard. Moving on to another
Sorry, question.
Yes, please.
So what is the input that goes into this one?
Input into what?
Extract alpha S. So what is the input given to the? There should be some masses or something that's input, right?
Yes. So the first, okay, the step scaling function is quite technical. Let me just explain the static quark potential method, where one simply determines the static quark potential with some really heavy quarks in it. The main basic thing that goes into input, basic thing is bare gauge coupling. That is,
Okay, all right.
yeah, I have.
Thank you.
So it means infinite quark masses. Yeah.
And sorry, you input the
Input it. Maybe I should clarify this. I have no contribution to these calculations, so I don't input it. To my knowledge, the bare gauge coupling is what is getting into the picture.
I see. Okay.
Which is also a function of the lattice cutoff. To technical, but one has to tune the gauge coupling such that some physical parameters are behaving as is expected in the continuum.
Okay. All right. Thank you.
Also, I guess it has the quark masses.
Okay.
These are ensembles, so one has to put in the physical quark masses.
Yeah. Okay.
One puts into infinitely heavy quarks and then sees what is the potential.
Yeah.
And since we know that the potential should be Cornell type, so from there one, I guess.
Okay. Thank you.
Yeah. So another observable is once again this kind. So the whatever slides I am showing for the time being, not all of them. Okay. In fact, actually, most of them are not really my calculation, but I am showing you just to motivate you how successful lattice calculations are. Okay. In this regard, the second slide is on determination of quark masses itself. Here is a screenshot from particle data group review. Interacting. You can see the web page. This is a screenshot from there, and you can see out of the latest 10 that or they consider for the world average. In fact, actually, they consider only world numbers till here, till 2010. Others are not considered. You can see most of them are lattice determination. Maybe I should mention this as well. This is all of these calculations, not necessarily all calculations are purely lattice. One cannot say this because these all have some inputs from effective field theory or some expectation in various different limits. This one example is what I and Chaitan also said earlier, that one expects at large distances, one expects to see a Cornell type potential. So from the alpha S is extracted. Similarly, here again, for example, Basavo et al., where they calculate the quark masses based on some HQET, heavy quark effective theory expectations. So these purely not entirely lattice, but still lattice is the main input that makes. And you can see the world average is mainly dominated by lattice numbers for quark masses. Similar estimates you can also see for D quark mass, S quark mass, and C quark masses. Okay. Moving on to the spectrum, which is the part that I will be mainly talking in the rest of my slides. Slide. This is a picture from a science article from BMW collaboration, where they have computed the light hadron masses, the ground state light hadron masses. The pion, the pion mass and the kaon mass are input calculation to tune the U quark masses and the D quark masses. Sorry, U quark masses and the S quark masses, because pion has a U quark masses or a U quark mass or a D quark mass. Kaon has a S and a light quark, D quark. So using those U, D and S quark masses are tuned. Here actually this is a pure QCD calculation and strong. There is also no effects from U and D quark masses. So basically U and D quark masses are taken as a sign. And from that they calculate the light hadron masses. So basically you can see here there are mesons, the pseudoscalar mesons, vector mesons, spin half baryons and spin 3/2 baryons estimations. You can already see they are quite successful in determining all of these ground state estimates. Of course, there are some of these cases are quite large in error. This is very clear because why these are large in later slides. Another example for such determination is heavy baryon sector. I show this particular sector. Okay, there are also estimates for mesons. I don't show it, just that I don't show it. I show heavy baryons because these some of our numbers, our determinations have also appeared in PDG review. This is again a screenshot from the PDG review, and you can see these are for doubly charm and triply charm baryons. One state that is observed by NB has observed this doubly charm, which is presented by this, while no other states has been observed, and all other numbers are lattice determinations. And you can see here our numbers have appeared here because so here this is something totally different.
Sorry, a question about the previous plot.
This one.
So yeah. So the width is here, the experimental width, is it?
Yes. These horizontal lines are basically the experimental numbers, and the band is basically the width.
Okay, and the lattice cannot compute the width, or can it?
Will be actually part of the discussion in later part of my slide. But there are some problems with it. You cannot means maybe I can just give a brief idea.
No, you can talk about it later. It's fine when
okay,
you come to it. Yeah, that's fine. Yeah.
Fine. Okay, so this is another set of. Okay, now let me move on to finite temperature. Here again, now this calculation I have no connection with, but since this is very important, and you can also see sign the calculation. I don't have any inputs in this part, but just to give a feel how successful it is in how successful lattice QCD calculations are in studying thermodynamics as well. Okay, so here what it is trying to study is the chiral crossover or the chiral change of phase. This is what I was saying in some of my earlier slide, where I said that okay, at some point in the hadronic scale, this symmetry is broken, while at high energies it need not be broken, or it could show. And this is what they have studied. By now we know that this is actually a crossover at finite, non-zero chemical potential. And what they have tried to study is to scan phase diagram, temperature and chemical potential, and they try to determine the chiral crossover region. The yellow band is what basically I really appreciate to see, compared with the experimental numbers for the freeze out points, these experiments. Okay. So this was said. I hope you all are motivated about. You all have got a feel of why I study subnuclear physics and why I use lattice QCD to study all these things. Now that I said all this much, let me just give you a brief feel of lattice QCD and how we do hadron spectroscopy using lattice QCD. Okay, very brief idea of lattice QCD. We put the gauge theory on the on a discretized space-time, which so basically this is a non-perturbative gauge invariant regulator. So here actually we put the quarks on the sides and gauge fields on the links so that there is a gauge invariance. The lattice spacing gives a UV cutoff for the theory, and lattice size, the size of the lattice, we put the lattice in a box. So basically the size of the lattice give you an infrared cutoff. Okay, remember the path integral, you can actually associate the path integral or correlate the path integral like a statistical system. So once you have a discrete space-time, you have finite number of degrees of freedom. Your infinite dimensional path integrals basically becomes finite dimensional integral. And if you stick within a Euclidean metric, then you can do Monte Carlo simulations using the Monte Carlo simulations of this system. Approach, you can study these systems very effectively. This is what lattice QCD is all about. Okay, we do spectroscopy. So once you have all this simulated data, so basically we have an ensemble. Can keep it aside. Now what we do is we construct 2-point current correlation functions on this ensemble and try to estimate their large distance behavior or large time behavior. You know, in large times it basically will be e raised to imt. So that basically means the time is actually Wick rotated, which gives an I component. So that basically large times the like an exponentially falling. It should have a exponentially falling behavior, and from that exponentially falling behavior, you can determine the mass of the degrees of freedom in it. Lattice way of saying it, one can actually determine get a feel of what will mass of the system by defining this quantity log of C of t by C of t plus 1. You can actually put C of t plus 2 times 2 here, which will also give you a feel, but this is basically to get a feel of what will be the mass. 2 is try to fit this correlation function with multiple time slices using nonlinear techniques, and then extract the mass of the system. So this is the way one extracts the spectrum of hadrons using lattice QCD. This much said, so it is very clear that the ground state can very clearly be ground state in the sense all those states that are low lying in any of the quantum channel that we are investigating. So they can be very reasonably well extracted. Why I say reasonably well, I will come to a point. There are various cases where which there are exceptions. That's why I'm saying reasonably well. Ground is very well. Now let's move on to the states of ground states. Summary plot. I mostly show the heavy hadron sector. You can, if you are interested in knowing about the light studies for these kind of systems, you can always look into one of the reviews that I quote in slides. So this is my own write-up for the Lattice 2018 plenary. You can also find studies for light hadron sector in this article. So a summary plot for singly charmed baryons, both half plus and 3/2 plus baryons. So lambda. So these are basically various different kind of baryons. Lambda C is a isospin 0. Means it should not have any. Isospin 0 baryon with a charm quark in it. This cascade C is isospin 1. Cascade C star isospin 1 spin half. Cascade C star is 3/2, and star is with a 3/2. Cascade C and Cascade C prime are slightly different. They both are spin half, and they both are isospin half. Isospin half. Yes. Omega C is where there are no light quarks in it. The horizontal bands, the gray bands, are basically the experimental numbers, and all of the others are lattice estimates. Can construct one can actually put QCD on the lattice in various different ways. various different ways means each of them will have their own systematics. Each of them will have their own various artifacts, everything. But still you can see that all these determinations in agreement with each other. Of course, there are some cases which are outlying, which we by now know why they are. There are some issues with scale setting, etc. But all others, for example, this you can forget about the red points, but all others you can see that they are quite in agreement with each other and also agree with the experiments very clearly. Okay, in this
Are these
respect,
results all in the continuum limit,
sorry,
or are these
sorry,
results all in the
no,
continuum
yeah.
limit?
So this is no, not all of them are continuum limit. So this is another. So lattice calculation should also be means all these these calculations does not use physical pion mass. On the lattice, you can actually work with various different pion masses. You don't need to go to physical pion masses always. In fact, actually, it is not easy to go to physical pion mass because the cost of computation becomes high. So many of these calculations don't use physical pion. Some of them just stick to that unphysical pion mass, while some of them does a chiral extrapolation. You should also do a continuum extrapolation where the lattice spacing is taken to 0. Most of these calculations does not do any continuum extrapolation. Only few of them do. The Brisino et al., if I remember, they do a continuum extrapolation. C does a continuum extrapolation, while hadron spectrum, which is our own calculation, ILGTI does a continuum extrapolation. Hadron spectrum do a continuum extrapolation. QCD also does not do a continuum extrapolation, but still you can see even with all these different systematics, expectations from large systematics, they do agree very well. This is with respect to a single
Sorry,
value. Yeah.
Sorry, that confuses me. So if you don't do a continuum extrapolation, continuum, how do you say it? Continuum limit, right?
Yes.
Then how can you compare with experiment?
Okay. It is yes, you cannot compare with experiment, but you can always say that there is error for means finite lattice spacing error that you expect. Okay, this is what people do. Still compare with experiments, right?
So, okay, although the pion mass is unphysical, it is reasonably close to the physical mass that you can directly compare, is it?
Yes, yes. Okay, there are also some other tricks that are involved in this kind of comparison. Tries to subtract out the unphysical heavy pion masses, for example. This is not generally done primarily in baryons, but at least in mesons we do it by subtracting out the heavy quark masses and then add back the experimental difference and then compare it with the experiments.
See.
What is the lattice spacing in this calculations?
Sorry? Sorry, I could not hear actually clearly.
Yeah, this lattice spacing in this calculation of the order.
Okay, so most of the calculations have lattice spacing of point. For example, the hadron spectrum collaboration. This is our own, which has a okay. This is a anisotropic lattice, in the sense that the lattice spacing around the temporal and the spatial lattice are different. Tell you the spatial lattice spacing here. It is 0.11 for me something. The RQCD has a lattice spacing of 0.08 for me, if I remember correctly. ETMC does a continuum extrapolation, if I remember correctly. The PAC-CS has 0.09 femtometer or something. It's of the order of 0.1 for me in all cases where there is no continuum limit performed.
Can't one try with another lattice spacing and try to see what is the effect? I mean,
yes. So this is what I said. For example, yes. Yeah, people have done it. For example, our ILGTA calculation uses 3 different lattice spacing. 0.12 femtometer, one is at 0.08 femtometer, and the third is 0.06 femtometer. And we do a chiral as well as continuum extrapolation. Wherever chiral is needed, we do a chiral extrapolation and a continuum extrapolation. And for the continuum extrapolation, have seen that there is an A square dependence.
Okay.
Okay, this is also technical. So ILGTI collaboration, we use overlap fermions which have leading corrections at order a square. Basically, we only had to look for order a square corrections, and there we see that there are order a corrections. Find that even though there is order a corrections, if your meter is sufficiently fine to these lambda c, all these things. For really heavy baryons like the ones that I will be discussing in these slides, for example, these things, the effect of this finite lattice spacing is very large. You have to really go close to 4 or 0.05 or even smaller. Okay.
Yeah. Thanks.
One interesting highlight in this regard with respect to this ground states determination and discovery of, or this is the first discovery, I would call this as the first discovery of a doubly charmed baryon by LHCb collaboration. It was in the year 2017. Left hand side I show the peak, the cross section, the scattering cross section peak of this. While on the right hand side I compare that number with all other lattice computations that exist basically in this past decade, and you can see all of them agree with each other. And let me just highlight you that all of these lattice calculations predate this discovery. So all of these are predictions, and they agree very well with each other, very well with the experimental number as well as between each other. This ILGTI and hadron spectrum collaboration, these are our own numbers determinations. Hadron spectrum does not, this HSC does not have any chiral or continuum extrapolation. Is done with a 400 MeV per mass, while I do a
question. I have a question. Wasn't there this old experiment which had seen this hints of the cascades double C?
I'm coming to that. Okay.
Yeah.
So you can already see that this is very well in agreement with the LHCb number. Nida has pointed out there is an old story of a discovery of doubly charmed baryon candidate which had a mass of 3519 MeV. Mined by Select. In fact, actually they have 1 or 2 published papers and 3 other proceedings. Out of these 3 other proceedings, they also explain that they also find for this, but none of the lattice calculations agree with this estimate.
I see.
Okay, and I don't have a plot right now, but if you simply look into those scattering cross-section plot from the Select papers, you can see I would not strongly favor this as a candidate, but probably as a statistical fluctuation, or maybe I am not so experienced in the experimental part. There are they have with a background of 3 or 4 events, they have a peak of events. I don't know. And there are also if they are to interpret that as a candidate, then they should also interpret some other points that are highlighting 8 or so as other candidates. I don't know. I'm not really an expert in this experimental part, but still I would personally prefer to see this as the doubly charmed candidate.
Okay.
Question favors this, that the one that was observed by Selects is a doubly charmed baryon. Okay, this is the whole story. Now, similarly, we also have predictions for other baryons. For example, doubly charmed. So this is a plot on the left hand side. Predictions which are which includes chiral as well as continuum extrapolation. Chiral wherever it is needed. For example, the cascade CB needs a chiral extrapolation for the others. We also have predictions for charmed bottom hadrons, which appeared in PRL in 2008. Okay, so this much I said, but really answer that we are really done with determining. Probably really not. If you look back into PDG, the particle data group tables.
Sorry, can I just interrupt?
Yes.
So again, what are the inputs that go into this?
Into inputs to be
The omega CC in extracting the mass.
CC, the charm quark mass is tuned using the eta C meson. So eta C meson is a charm anti-charm meson with pseudoscalar quantum numbers. This basically has a very clean signal which is used to charm quark mass. This is an input. Light quark masses and strange quark masses. This is actually a mixed action calculation. So in the input for bare gauge coupling, for the light, the strange quark masses and the charm quarks. So these are three different inputs. And also, since this is a mixed action calculation, that basically means the ensemble generation uses a different fermion action than the measurement case. So in the measurement, we use an overlap fermion. For example, if you look into the omega CC, you have a quark flavor of C, charm and strange. So we basically had to tune charm and strange quark. So charm is tuned by eta C, and the strange is tuned by something called as a fickle eta.
Okay. Sorry, where is the strange quark in this thing?
The omega CC, so this is a baryon which should contain 3 quarks in it.
Yeah.
This is a doubly charm baryon, so that basically means 2 of the quarks in it should be charm. The third quark is a strange quark.
I thought the previous plot showed plus plus, no?
Which one? Sorry?
The omega plus plus different, is it? Oh, that's the cascade. Sorry, I was thinking of the cascade. Okay, all right.
Cascade.
Yeah, okay. Got it.
Yeah.
Thank you. Yeah.
So then I move on to looking into the PDG tables. A summary of Meson excitations from PDG. Told you were primarily for those states that are inside these cyan lines. Okay, these are strong interaction stable hadronic resonances. That basically means whenever they decay, they strong interaction. They need some other interaction like weak decay or so. Okay. All other states that are observed, all other excitations that are observed, purely via strong interactions. Okay, this is very crucial for later part of the discussion. But the main message here is that we are really not done with the spectrum because there are many excitations that are still to be extracted from first principle. Okay, scenario is not different for baryons as well. Here again, for baryons, I summarize the situation. You can see there are a few levels that are enclosed inside the cyan rectangles, while most majority are inside the red rectangles. Now, if this is the case, the question is, can we really get excitation spectra from lattice QCD? Yes, we can do it. The methodology is pretty much straightforward. How we do spectroscopy earlier. Now we can slightly extend by computing a correlation matrix. I also gave a field in my earlier slide where I put an IJ index. Can compute a matrix of correlation functions rather than only a correlation function. Do a variation analysis of this matrix so that we extract or we get the physics as a linear combination of whatever that we use. So we basically try to do a variation analysis. We follow a variation up to get the physical state information. So here, this is what is depicted here. So we construct a matrix of correlation functions. Try to solve for the eigenvalue problem for this matrix, from where we get eigenvalues, which gives you the information about the energy spectrum, while the eigenvectors gives you information about the quantum numbers of these. I'm not really getting into detail because this will become more. Yeah. Please.
What is the difference between phi I and phi j?
Where is phi? Okay, on the top. Yeah. So Okay, maybe I can go back to this slide because this is more informative. So this is the correlation function that I started with for studying hadron spectroscopy. Ij can be so the bar. So this is a creation operator and this is an annihilation operator. You can, for the time, if you forget about I and j here, phi is the corresponding creation operator is phi bar. It's up to us what whether we need to use the same kind of operators at source and the sink. So you
Can
can
you give an
always,
example? What do you mean by the same type?
this can be, okay, same type. For example, you can actually use an interpolating current for a pseudoscalar and a vector, a pseudoscalar at the source and vector at the sink. This will be zero because the quantum numbers are not the same. But you're free to use an interpolating operator for a pseudoscalar, interpolating current for vector here. Now, if you look into pseudoscalar, you can also construct pseudoscalar interpolating current in various different ways. Yeah, I have to. Yeah,
Okay,
you can
no,
construct.
no, I get it. You can still see signature in the correlation function. Okay.
Yes, yes. So the main idea is you construct interpolating a large basis of interpolating operators. You can always construct interpolating operators of different kinds, but still having the same quantum.
Okay.
So what I mean by I and j index runs over various of these kind of operators. Point is actually, since all of these have the same quantum numbers, they basically will, these interpolating currents will try to give you information about the physical states as a linear combination, which is a more sensitive procedure. Sensible procedure, I mean. Yeah. Okay.
But if you have same if I and j, I mean these operators are same, still you have some excited states contributing to the correlator, right?
Yes, yes, this is true. So this is one way one can do. So one can actually try to do a multi-exponential fit. This you can already. So this is so whatever is shown here is basically the effective mass. Now you can try to do a multi-exponential fit and try to get the E1 or higher excitations. But the thing is, once you have more and more parameters into your fit, the fit become very much unstable.
Okay.
Lattice calculation. If you are going to early time slices, it becomes really difficult to extract the excited state on a multi-exponential fit.
Okay.
So you need something different, and that's why we actually construct metrics of correlation functions instead of simply correlation function.
Yeah.
There are actually technical details that I simply skip because that takes a lot of time. I believe I am already taking too much of time. Yes, I don't know. Yeah, I have 20 more minutes, right? No, probably even less.
10
yeah,
minutes, maybe.
so 10 minutes. Okay, sorry. So by this way, why we have matrix of correlations from these. After solving the eigenvalue problems, we get the excitation spectrum. As an example, I show you the charmonium spectrum, which we determined back in 2018. These kind of calculations are not just restricted to heavy quark systems. You can see a lot different kind of mesons as well as baryons studied using this approach. So here I show you an example for the charmonium spectrum. I also show you an example for excited heavy baryon. So this is a plot for omega excited mesons, baryons. In fact, actually, these kind of calculations only we have done it. There are no other calculations for excitations of charmonium baryons, which the publications on this is spreading from 2013 to 2018. While for bottom baryons, there is only one calculation for triply bottom baryon, while there are no other calculations. But for light baryons, there are some other calculations which I am not presenting here, but you can actually find it in my review. So why I show omega c is because again of interest from experiments. There was a discovery by LHCb back in 2017, where they found 5 new omega c kind of states with very small widths. Okay. Now this was again confirmed by Bell. Now that we have some experimental numbers to compare, one can simply compare with our lattice numbers. here I make this comparison. So there is a half plus and a 3 half plus state that was observed in the past itself, while these 5 are the new states from the experiments, which is compared with the lattice numbers. And you can see that there is quite good agreement. Okay, our calculation is really exploratory. This is very much with very little statistics and also with a very heavy pion mass. But pion mass has relatively less role here because this is an omega baryon, which does not have any light quarks in it. So this we are fortunate to have a good comparison, and you can already see